All right, let's go ahead and get going. Any questions about anything at all before we get started or get back into this? Okay, I think there's written homework due tonight, right? Okay. I just posted the next one as well. I won't be doing until after the test. But I do recommend at least looking at it, or at least like working through it, because it does have some stuff from section 6.5, which we'll be covering on Monday, or we're covering on the test on Monday. Cool. All right. So back to improper integration. So to find this integral, based on what we did last time, how can we set this thing up?
It has a limit.
Has a limit. So why do I need to set it up with a limit?
Infinity is not a real number.
Right. So infinity is not a real number, but it is one of our bounds. So we're going to set this up as a limit from 3 to t of this integral 1 over x minus 2 to the 3 halves. Okay. So yeah, setting it up with the limit. We don't want to treat infinity like a number because it's not one. So how do we go from here? Solve. How so?
X minus 2 plus u.
X minus 2. What's that? What's that?
You can't use substitution.
Yeah, we can set up a substitution. So you wanted to use what for you?
X minus 2.
Okay, so if we set this up with a substitution, u equals x minus 2, then what is du?
Yeah.
Dx, right? All right, so now what does this integral become? The limit as t approaches infinity of, I'll keep these as make sure that we know these are still x values and not u values. So this integral becomes what? We're going to take the antiderivative of that now. Go ahead.
Yes, you could have negative 1/2 over negative 1/2.
Good. Okay, so I'll write down both of those steps. So as x goes from 3 to t. Oh no, I don't need that anymore. So u to the negative 1/2 over negative 1/2, evaluated from x equals 3 to x equals t. So that becomes negative 2 over square root of u from x equals 3 to x equals t. All right, so let's stop. Any questions about how we ended up with what we have right now? Go ahead.
I'm confused, like, how the u to the power negative 1/2 and over negative 1/2.
Okay, so let's take it one at a time. Let's take the exponent first. Raising something to a negative exponent. So if I raise something to a negative exponent, what am I really doing there?
1 over.
So yeah, so that was going to be my next question. So if we want to write that with a positive exponent, we really are taking the reciprocal. And then the power of 1/2 is identical to square root of u, right? Okay, so that's why that square root of u winds up in the denominator. Why do we have a negative 2 in the numerator? So that comes from the other part of this, which was negative 1 over 1/2. So how do you divide by a fraction?
Oh, you get the one on the bottom.
So instead of, yeah, dividing by a fraction is equivalent to multiplying by it. So that's why I have a -2 in the numerator and a radical u in the denominator. Make sense?
Yeah.
All right, good. Go ahead.
Did you have to reset your balance?
We could. That's why I've been writing x equals is to make sure we realize that they are not the version we're going to need. So let's take care of that now. What should my bounds become then? So the limit is t goes to infinity of this -2 over radical u from
One,
u equals 1. How'd you get that?
plug it into the u in terms of x.
Okay, so if u equals x minus 2, then if x is 3, then u is 1. What happens to that t?
Stay as t minus 2.
Should be t minus 2, right? Which is kind of weird because we're going to let t get as large as we want, right? That's okay. So now we can start evaluating the integral part of this. So the limit as t goes to infinity of -2 over square root of t minus 2 minus -2 over 1. All right, so now we've evaluated the integral. The last thing we have to take care of is the limit. So we're going to have something plus 2 essentially, right? What's going to happen to that first term as t gets really, really large? It's going to go to 0, right? So you're taking the numerator, which is constant, and think of yourself, you're dividing it by things that are going to get large without any kind of upper bound. So this comes out to be, where's my cursor? 0 plus 2. All told, the answer is 2. Any questions there? We happy so far? Relatively? All right. Oop, I go too far. All right, so now I've got something improper on both bounds of the integral. Any ideas how we need to handle this? So when I set up a limit, I can only have it go. I can only evaluate a limit as it goes to like one value or one like idea, right? Go ahead.
Can we do t equals infinity and then set the balance to t and -t?
So what you're saying is, so it has a limit as t approaches infinity, and have this go from -t to t.
Yeah.
So basically, we're using the fact that even though the upper and lower bounds, they're different, but I can set up t to kind of capture them both. The only problem with that is if we do that, we're assuming that the function is like symmetrical on both sides of the y-axis, which it might be, but I don't know for sure. So this actually, basically, we're asking too much of our value of t when we do this. So an intermediate step I'm going to throw in here is this. I'm going to break this integral into 2 different pieces. So I'm going to have basically the left side of it, like graphically speaking, that goes from -infinity to something. And the right side of this that goes from something to infinity. Does it matter where we split it in the middle? It doesn't really matter. As long as we don't leave any like empty space, like, for example, is this okay? No. So as long as I let the upper bound on the left agree with the lower bound on the right, choose your favorite number. 0. Probably logical. So if I add these two things together, that should give me what I want from this integral, right? And now I'm letting one bound of these integrals be fixed and real, and I'm letting the other bound of this integral be the thing I have to deal with. I just have to use a limit to deal with. So let's do one at a time. So the limit as t goes to infinity or negative infinity of t to 0 of x e to the negative x squared dx. Is this an integral we can do? How do we attack it?
We do integration by parts.
Integration by parts. I think that would work, but I think there's more direct way.
Use substitute.
Okay, why use substitution? Why am I pushing back on by parts and picking substitution?
So if you do like parts, we're gonna just be like the same thing. And then just repeat, because of what me.
So here's the thing with integration by parts. Let's say we go down that route and we do integration by parts. What do you want to choose for u? What do you want to choose for dv? Yeah, I said I thought the integration by parts would work. Now I don't think it would. So let's figure out why I'm saying that. What choose something for u, some part of that function. If I choose x, then you put e to the negative x squared over here, right? So this derivative of u will definitely get simpler. But then you have to integrate e to the negative x squared dx, which is not something we know how to do. So we can't integrate e to the negative x squared dx. So what happens if we put it over here? You can take a derivative of e to the x squared, but then you're going to integrate x, which is going to give you more powers of x. So I don't think integration by parts will get us there. I heard some people talk about substitution. What substitution would you like to make for u? Negative x squared. So then what's du? Negative 2x dx. Let's figure out the limits as well then. If x equals 0, what does u equal? Still 0, so that one's not going to change. If x equals t, wait, sorry. Yeah, if x equals t, then what does our lower bound equal?
Negative t squared.
Yeah, it should be negative 2 squared, right? All right, so what's the integral? It is, oh yeah, we still have to figure that out. So it should be e to the u is part of it, right?
Yeah.
Can I deal with dx directly?
-1.
I think x dx is equal to this. Negative 1/2 du. Go ahead.
Did you put the negative t squared in there?
Because so that comes from this thing here. So I have this formula that translates between x and u. If x equals 0, that means that u equals negative 0 squared. And if x equals t, that means u is equal to negative t squared.
Okay.
So all of that to basically the integral I gave you had bounds for x. If we're going to translate our integral into being in terms of u, we need to translate the bounds as well. So I think we've done that with our integral. It's all ready for, well, substitution's done. Now it's ready for integration. Can I take that integral? What does this become? What is the integral of e to the u? E to the u, right? So this whole thing becomes 1/2 e to the u from negative t squared to 0. So if I plug in 0 for u, I get negative 1/2 times 1, right? And then minus negative 1/2 e to the negative t squared, right? I feel like there's a sign flip somewhere. Because I think if you plug in negative infinity, that e is just going to get larger and larger and larger, right? But I expected it to converge, so I feel like I got a sign flip somewhere in here.
I don't know if it gets large. Oh, yeah. Because if you plug in a negative infinity, where it's still be negative infinity, you did negative infinity power.
Oh, you're right, because I'm squaring it. You're absolutely right. Okay, never mind. So it does converge like I expected it to. So yeah, if I let t get larger if I not larger and larger, t is going to basically go far left. It's going to take on these these numbers that are very large in magnitude but negative. If I square those, they become very large in magnitude and positive, right? But then they're still going to be multiplied by that -1. So I think, yes, the term on the right is going to trend to 0. So what do I get? Just negative 1/2, right? Okay. Are we done? No, that was half, but really we've done a lot of the hard work to find the other half. So we have found the integral from negative infinity up to 0 for this function. Now we got to find the integral from 0 to infinity, right? So the limit is t goes to infinity of the integral from 0 to t of x e to the negative x squared dx. But we've already done a lot of the hard work on this thing, right? It's going to have the same antiderivative, but I think we need to change the bounds. So the limit is t goes to infinity of negative 1/2 e to the u du. I'm going to reuse all your same substitution stuff from last time. But now what are the bounds going to be? But now that I'm in u,
T squared.
should be negative t squared, right? So it looks almost identical to what we just did, except the bounds are reversed. So the limit is t goes to infinity of negative 1/2 e to the negative t squared minus negative 1/2 e to the 0, which is 1. So that's going to come out to be what? 1/2? Okay. So what's the value of our integral? 0. Isn't that disappointing? So this thing equals 0. So if we would have broken that down the middle somewhere else, we might have gotten different values for the individual integrals, but they still would have canceled out. Any questions on this one that we had to basically split the two? What about this one? So we're gonna have to split this one in half again, right? You want to split it to 0, or should we do something else? 0 again? All right. So the limit as t goes to infinity of, let's do the positive side first. So 0 to t of 1/1 plus x squared dx. Is this an integral we can do? It is. might look familiar to some of you, but this is, yeah, this integral is kind of one of the stock, even though it's you don't see it all the time, but this is simply arctangent. The limit as t approaches infinity of arctangent x from t to 0 or 0 to t, which is equal to the limit as t goes to infinity of arctangent t Are you gonna get mad at me if I change my notation to safe space? Do we know what the arctangent of 0 is? What does arctangent mean? So like if I say y equals the arctangent or the inverse tangent of x, what does that thing say? Where does the tangent of what? So basically, if it's an inverse function, which means we can invert it, this is the same as saying tangent of y equal to x, right? So in both cases, y is some angle, and x is whatever the tangent measurement of that angle is, whatever the tangent value of that angle is. So having said all that, what is the arctangent of 0?
0.
Should be 0, right? The angle that has a tangent of 0 is 0, so this basically vanishes. What happens to this thing here as the angles get really, or not the angles, as the tangent measurements get really, really big? Yeah, you're doing this. What's that?
It just kind of oscillates between values and never really goes.
I don't think it oscillates. I think you're thinking what happens if the angle grows, but that's not what's growing. Yeah, you're right.
Oh,
If you like, if it was like y equals tangent x, if you let x go on forever, it just repeats. It repeats its cycle, right? So let me try to draw you a really clumsy diagram of what's going on here. Let's think of right triangles. The tangent of this thing is going to equal t, right? So here's my angle. I'll call it y. If the tangent is t, can't I say that I have t over 1 as the opposite and adjacent sides? Are you believing me so far? So now basically what I'm asking you is think about what happens to that angle if I let the height of this triangle just keep growing. What's that angle doing? So it's opening up, right?
closer to 90.
It's going to get closer and closer to right. So it's never going to actually achieve a right angle, but that's its limit. If I were to let that height of that triangle grow as large as I want. So because of that, this limit is 90 or pi over 2. So basically what's going on here is I'm letting t get larger and larger. So it's not possible for that angle to ever be not pi over 2, but I can get as close to pi over 2 as I want, as long as I don't ever achieve it. Any questions about the logic of that? Why this arctangent is pi over 2? Okay, we done? No. We need the other side of this. So the limit as t goes to negative infinity of t to 0. Even though we split this up, we get to use the same antiderivative. So this will be equal to this limit. The limit as t goes to negative infinity of arctangent t from t to 0. So again, arctangent 0 is still 0, right? Now, if I let t get really, really small or go to very large in magnitude negative numbers, what happens to that angle? So basically, if you go back to my triangle diagram, I am now basically sinking this side here. I want that height to like basically go really, really deep. So what's happening to that angle? Y now? It's also going to go towards a right angle, but you don't call it 3 pi over 2. So think back to, I don't know if you touched this in Calc 1, but probably pre-calc or some other time, but the inverse trig functions, they have very limited ranges. So if you take the inverse tangent of an angle, it's basically the highest you can get from that is pi over 2. The lowest you can get is negative pi over 2. So because of that, I mean, you're looking at the right place. 3 pi over 2 is that negative y-axis, right? But because of the way the inverse tangent function is structured, we get this coterminal angle of negative pi over 2. So because of that, what's the value of this integral? So it should be pi over 2, 0 again, right? Oh, wait, no. Okay. This comes up to positive pi over 2, right? Why? Yeah, we're subtracting that. So it should be pi. That's okay. Pi over 2 plus pi over 2, and that's equal to. Any questions there? Maybe.
When it's still be negative,
I don't think so because
it's still a tangent.
So this arctangent right here goes to negative pi over 2, right? So as t goes to negative infinity, the arctangent of t goes to negative pi over 2, right?
It's 0 minus negative pi over 2.
Yeah, that's why it becomes positive. Is because we have arctangent 0 minus arctangent t. So in this case, for the integral I'm doing in the bottom, the second one, as t goes to negative infinity, arctangent of t goes to negative pi over 2. But what I forgot to do the first time was to subtract that from the value we got from arctangent of 0. So basically, I flipped the sign. This should come out to be positive pi. Go ahead.
But don't you subtract like the two limits? Why are you adding them?
So you're right that I subtracted 2 limits, but are you asking about like why I'm adding pi over 2 to pi over 2?
Yeah.
Okay, so that is not the same thing. That is not me subtracting the limits for each other. So basically what's going on here is this. We can split up integrals right down the middle, which is what we did. So this integral from negative infinity to infinity is equal to the integral from negative infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. So 2 different things going on here. Yes, when you evaluate a definite integral, you have to subtract your antiderivative evaluated at the limits. You find the difference of those things. So
Separate them, you add them?
yeah.
Oh, okay.
So basically what I'm doing here is think about the rationale used with the Riemann sums. With a Riemann sum, you split it up into areas, you find all those areas and you add them all together, right? I'm kind of doing a more complicated version of that. I'm treating my integral as 2 integrals that should add up to give me the same area. So I should add them together. So this come out to pi over 2 plus pi over 2 equals pi. But yeah, so I mean, all that to highlight that it's important to know not only that we're adding in one situation and subtracting in the other, but why we're doing this. So if I'm adding together two integrals, or like I'm trying to find a combined area, then we need to add those areas together. If we're trying to find the difference in the bounds of that integral, that's a subtraction. Anything else about this example here? How about this thing? Why is this thing being classified as an improper integral? I don't have infinity in either one of my bounds. They're both real numbers, 2 and 5. So what's the problem here? What's that?
You get 1/0.
Right, so this function is not even defined over the full interval, right? So it's undefined at the left end of it. So basically everything else we've looked at has been these, we're trying to find areas of things that basically have infinite length, right? So now if I draw a quick graph of this thing, so the square root function, oh, it's 1 over the square root function. So it's going to be undefined at 2. So it's going to have this like vertical asymptote near 2. So basically the area I'm trying to find is like this. So how tall is this weird shape going to be? It's going to be infinitely tall. So it has infinite height, but it still might have finite area. So that's what we're going to find with this integral. How do we evaluate this integral?
What do you mean by finite area?
It means that it converges, or basically, let's do an example we already did. So I didn't draw this. I guess I could right now in what little space I have left. So I was integrating this from negative infinity to infinity, right? If I can draw a straight line, I'll draw you a graph. Good enough. But basically what this function looks like is when x equals 0, it equals 1 here. So basically it's going to have a maximum at the y-axis and kind of slope off like this symmetrically on either side. And we're trying to find that area. So we found the area, right? The area was finite. It was pi. We were able to measure it with a real number. But how long is that region? It's infinitely long in both directions. So even though one of its dimensions can't be measured, it can't be quantified because it's infinitely long, the area can be. So basically it's a shape that has infinite perimeter, but limited area. So we're trying to see if this area underneath this square root curve is the same kind of thing. It has infinite height, but it might have an area that converges to some real number. So how do I deal with this integral of 1 over radical x minus 2? U substitution? What do you want to use for u? If u is x minus 2, then what's du?
Yeah.
Du should be equal to dx. Should we deal with the limits as well? What are the limits then?
2 is 0.
So right, basically we're sliding all of our x units, or we're decreasing them all by 2. So our bound should now be 3 or 0 and 3. And we're integrating u to the negative 1/2 du, right? That looks a lot more manageable. What is the antiderivative of u to the negative 1/2?
So we could be 1 over 2.
Square root of u over 2. I think it should be square root of u times 2. Because the square root of u over 1/2, right? Yeah. So let me stop there for a bit. Any questions on how we got here? Go ahead.
So I'm a little confused why you subtracted both by 2.
Sure. So it all comes back to the way we define the substitution. So right here, so Saul suggested we use a u substitution and to use u equals x minus 2 for our like intermediate function. So once you do that, so that helps us do 3 things. That helps us re-express all of our basically our integrand, the function we're trying to integrate in terms of u. So that's why 1 over square root of x minus 2 became 1 over square root of u. Du and dx are identical, so that means I can just swap one out for the other. The third thing it does, and only if we're dealing with a definite integral, is it takes these bounds, which are, even though we don't write this, these are x equals 2 and x equals 5. So the integral I really want to do is to evaluate over this x interval from 2 to 5. But now that we've rewritten this integral in terms of a completely different variable, I'm not integrating from 2 to 5 anymore. So how do I translate those x values to u values? I can use the same rule that my entire substitution came from, which was u equals x minus 2. So basically what I'm saying is that whatever you choose for your u drives everything. It's powerful enough to change everything in the integral. So we can do it. All right. Anything else? Or are we good to do this, to finish this one off? So what is this going to be? What's the value of this going to be? 2 times the square root of 3 minus 2 times the square root of 0. So infinite height, but the integral converged, so I have a finite area to that. Go ahead.
What's special about this one?
The fact that so the function is not even defined over the entire interval you're trying to integrate about. So you're asking what's special about it. I think you're getting like, we didn't really treat this any differently. Like let's say the integral was from 3 to 6. Is this function defined everywhere on that interval?
Yeah.
Would we have handled that integral any differently? No. So I think that's what you're getting at when you're asking what's special about it.
Yeah, well, like, so what's the discontinuous part?
Yeah, why do I call it discontinuous?
Because it never touches 2.
Right, so this function is not defined at 2. This function is not continuous at 2.
Okay.
So-
It doesn't change it.
Not this time. But that's something you have to look out for, is that it's very possible for this integral not to be, like for integrals like this not to be defined. So there are integrals where the region you're trying to find the area of has infinite height and the area is also infinite. This is not one of those times. Okay. Same kind of thing here, or not the same, but we have a problem here. So think back to Calc 1. This probably came up, but very briefly, because we kind of just make some assumptions with integrals, but we know that continuous functions always have integrals. If you have a function that's continuous over an interval, its integral has to be defined. As long as that interval is closed. Like, so it's like it actually has real numbers on both ends. Once you have functions that aren't continuous, you can't make that guarantee. So is this function right here continuous on the interval I'm trying to integrate it on?
No.
Why not?
Because it doesn't exist in 2.
Right, it's not even defined at 2. It can't be continuous at 2 if it's not even defined. So because of that, we have to break this thing down. like this. And the other ones we were dealing with infinity, we had some choices about where to make that that partition. We don't really have a choice here. I'm going to break this up into two integrals, one from 0 to 2. And one from 2 to 3.
It's squared.
Yeah, thank you. So it's clear why we have to break this thing up. So I think the impulse for many of us, and the first time I saw one of these, I probably would have done the same thing, was just, all right, I know how to find antiderivatives of this thing. I'll just find the antiderivative, plug in 3, plug in 0. Subtract them, and that's my answer, right? But doing all that assumes that your function is actually defined and continuous over that whole region. So this one, if I'm integrating from 0 to 3, 1, 2, 3, 2 is going to be an asymptote. And basically on either side of the asymptote, since I'm squaring, it's going to get really positive and big. So basically I'm trying to find 0 to 3, right? I'm trying to find this area right here all the way up. So again, we have something with infinite height. It's only 3 units long, but it gets arbitrarily tall. We had the same sort of thing with our last example, but that one converged to something. Now we need to see if this one will. Any questions on anything? Or are we just good to go? So let's deal with the one on the left first, the integral from 0 to 2. How do I integrate things like this? People like u substitution. What's u equal to?
X plus 2.
X minus 2. Du is equal to
X.
x. All right, let's have the limits. If x equals 2, then what does u equal? U equals 2 minus 2. And if x equals 0, then we have u equals 0 minus 2. So all of that gives me the integral from -2 to 0 of u to the -2 du. What is that antiderivative? -1 over u. From -2 to 0. How are we doing? Is this going to work? No. So what did we learn about the area for this one? It's infinite. It doesn't diverge. So this integral diverges. Is it okay that I'm not even looking at the other part of it? Go ahead.
So what would be right the present answer?
That it diverges. There is no there's no real number that we can get from this integral.
Okay.
So for me, the web work, I think the web work probably tells you to answer, use the word diverges or div or maybe dne for does not exist or inf. Basically, all of those things are equivalent ways to say that the integral gets infinitely large and does not converge.
Why can't we write infinity one?
You can.
Please.
Would you rather? I'll say this. I'm not going to say equals, but I'll put an arrow to it because it approaches infinity. I don't want to treat infinity like it's a number, but essentially this integral does not give us a real number. Questions? We'll get as far as this one as we can. We only got like 4 minutes. So how do I set this thing up? 0 to 1, 1 to 9. How come?
It's undefined.
It's undefined. So this is not continuous on the interval. So I need to break this up into these two integrals. So if both of these sums converge, then my integral will converge. So let's pick them up one at a time. How do I find the integral of radical x minus 1 dx? Go ahead.
It's 1 over.
Yeah, otherwise this thing doesn't make sense. Repair. Thank you. All right. I think it's fixed. So how do we handle that integral? U substitution. It's always solve. That's the so that definitely works. Du is equal to dx again, right? What are my bounds? Negative 1 to 0 of u to the negative 1/2 du. What's the integral of u to the negative 1/2? Should be 2u to the 1/2. Is that going to work? No. Why not? So this function, like it's not continuous over the whole interval, just like this one was not. But how many discontinuities were on this interval here? Like how many x values is that function discontinuous for? Exactly 1, right? How many x values is this one discontinuous for? There's an infinite amount of numbers between 0 and 1, right?
Yeah.
So we can handle maybe we can handle like a few, like finitely many discontinuities, but not when the interval just has infinite numbers of discontinuities in it. So how would a graph of it look? It looks really silly if you look at a graph because this function looks like this. And I'm asking you to integrate it back here. Like I can't talk about the area under that curve because the curve doesn't even exist between the y-axis and x equals 1. So this one does not exist either.
Okay, can you go back to the last one?
Yeah.
I don't feel like a graph. I wanna.
Yeah, top right. So basically, at x equals 2, you're gonna have vertical asymptotes on both sides. If it was just 1 over x minus 2, you would have one going towards negative infinity and one side going towards positive infinity. So since we're squaring, that's why they're both. You get that cone. All right, that is all for 6.5. So just a reminder, I'm not gonna have much prepped for Friday. I gave you lots of stuff that you can like review on Canvas, past homeworks, web works, written homework, all that stuff. I am happy to answer whatever questions you have on Friday. Whatever you want to talk about is fair game. Because Monday I'm just gonna drop the test off, which as soon as 9:05 happens, you'll have the whole time to work on it. Go ahead. Go ahead.
Like we have to identify like whether it continues or not. Right?
Yeah.
The test is handwritten or
Handwritten.
Okay.
Yeah.
How many questions do you have?
I think it is 8 multiple choice, 3 peer response.
Maybe at 50 minutes.
Yeah. I don't think we protocol out of 9:55, but. Yeah, let it go on forever either. I don't think there's a class after y'all. So no one's gonna be trying to throw us out, but. Maybe 55 minutes. Depending on how things go. But yeah, as soon as 9:05 hits, please be here. Pretty much all of you are all the time, but. Especially that day. What else? Go ahead.
Can we use calculators?
Absolutely. Yeah.
We can use.
Yes, calculators are good.
And graphing or just saying?
Yeah, traffic. As long as it doesn't, if you see the words, the letter CAS on the top of it. Those are out, but otherwise they're fine.
Do we need a graph then or would a scientist?
I'm not gonna say you need. Scientific calculator ought to do it for you.
Look, I mean, we wouldn't have to graph any function.
No, I'm not gonna require that. I mean, you're always welcome to do it if it's gonna help you, but. I will tell you right now, I'm not specifically asking you to graph anything. I haven't asked for that in anything so far. So it might help you, but I'm not gonna require it. So.
Are you able to set the candidates like, exam review to like, do not have a time limit because,
Is that time limit?
yeah.
Oh, yeah, I'll take that off. I didn't mean to. Yeah, I'll make that change with it. What else? Nobody has to stay. It's 9:55. I'm just kind of like answering questions. I'll be in office hours. I'm probably gonna go right up there straight from here. Otherwise, I'll see you Friday.
Just for this A211 assignment, I have to like about.
Yeah.
Just help them write something down.
I got you.
What's the advice just to pass it?
I think the biggest thing that I kind of suggest people, even if I hadn't said the whole group, is something I wish I did when I was an undergrad is. When I was an undergrad, I did not like review my notes and study for this, like for any specific class every night,
Okay.
even if it's just for like half an hour.
Mhm.
I think that's a really good idea, because I think what most people do, what I used to do is 3 days before a test, okay, now I'll start studying.
Yeah.
Which is not maintained, like it's hard to maintain that and hard to sustain that. So I think that's something I didn't start doing until I got to grad school, and I wish I would have started doing a lot earlier. That's my next.
All right, thanks.
That was.
Transfer over to the
What's that?
scratch papers.
I'm not gonna provide scratch paper. There should be plenty of room for you to do your work, but yeah, if there's not.
Because they have like big balance for the scratches, but it's not having like it's a plain or something.
Yeah, I mean, it should be plain paper.
Like
I'll ask you to turn it in with the test,
Ah.
but I mean, otherwise you're free to bring something inside. Of course.
How many trade integrations are we gonna be using? Just like basic.
Yeah, certainly the basic like. Sine integrations, sine and cosine certainly. We have done tangent and cotangent kind of like as. We've set them up using U substitution. So if you look back to our, like when we first did substitution.
Yeah.
We probably did that. What else? But like secant